today, let's follow up on something that was mentioned last time. So strongly regular graphs. And this is always a popular topic. And, well, there's not too much to say insofar as it's not so terrible to actually compute the spectrum of these graphs. So we first have to say what are strongly regular graphs, and there's a set of parameters for them. So we'll just SRG for strongly regular graph. You have n, k, lambda, not to be confused with lambda the eigenvalue, and mu, where n is your number of vertices, k is your degree, lambda, well, I'll draw a picture, just to sort of help you understand what's going on. So you pick two adjacent vertices. So here's u and v, they're adjacent vertices. And then what you look at is you look at their common neighbors. So you look at the intersection of their neighborhoods. And what you'll see is that there will be lambda vertices down. So every pair of adjacent vertices has lambda vertices in common as their neighbors. And then mu is similar, but instead of adjacent vertices, you're going to take non-adjacent vertices. So that is to say, you pick any two non-adjacent vertices, look at their common neighbors, and you'll say, they have mu of them in common. So mu vertices. Okay, good. Now, one of the things that pretty much is automatic is that there tend to not be very sparse in some sense. And in particular, we can say the diameter of any strongly regular graph is at most 2. Which is to say you're never more than 2 steps away from any other vertex. So, all right, good. Now, you might say, why is that true? Well, suppose diameter was 3 or higher. Let's start with 3 or higher. So what would happen? So suppose u and v, you actually had to work hard to get from u to v. All right, well, how many common neighbors does u and v have?
It has the same number of neighbors as the one closer.
Well, right, that's going to be my next observation. But u and v right now, if I have to take 3 steps to get from u to v, they have no common neighbors. But if I were to go 1 step closer, there'd be 1 common neighbor, meaning that there is not a single value for mu. So I can't have things 3 steps or more apart and have them be consistently having a consistent mu value. All right, so that says, all right, these graphs you don't go very far. Now, okay, well, that's one thing. Do we know any examples? Have we met any examples of strongly regular graphs?
Yes.
Okay.
Like the one that was in our last homework problem.
The Peterson graph?
No, I was thinking of the other one. But since you said
that disaster with
Yeah.
all of the edges.
with the 16 vertices.
That's not bad.
I don't know if that's strongly regular. It might be.
Oh, okay.
I didn't check. The complete graph. Okay, we'll start with the complete graph. So the complete graph is in fact strongly regular. What would the parameters be if I have a graph on n vertices? The degree? n minus 1. Lambda? n minus 2. Mu? Haha, trick question. Doesn't matter because there are no non-adjacent vertices. So you can say it's anything and it works. All right, so it's not a very fun example in that regard. You know, dealer's choice. All right, so maybe something a little less trivial.
How do you phrase the sentence here? Would you say the complete graph is SRG of this? Or?
Right. Well, I would phrase it as the complete graph is strongly regular on n vertices, degree n minus 1, and any two adjacent vertices have n minus 2 neighbors in common. And then I just wouldn't even bother to talk about non-adjacent vertices, just because we'd all understand there's this sort of vacuousness going on in play. Yes?
Sorry, degree is the same thing as just regularity?
Right, yes. So it's not just regular, it's strongly regular. It's just like, yes.
Yeah, the first two parameters are just.
It's like those streaming services, you know. It's not just this, it's this plus.
If you have a non-regular graph, does that have a degree? Or we just talk about the degree of various vertices?
Well, so for non-regular graph, there's not like a consistent degree. And so you might talk about the average degree. That's usually something you would talk about. There's, I don't know if you ever have heard of something called highly irregular graphs. No.
Like every vertex has a different degree?
Ah, is it possible for every vertex to have a different degree in a graph? All right, and there's people shaking their no. It's a good exercise, but you can show that in fact it's not possible. And so I think the most common definition, if I recall, is it says a highly irregular graph is one where all the degrees in closed neighborhoods are distinct. So there's just like around you, everything looks different. No two things look the same based on just their degrees. So locally, nothing has the same degree. Now, the story I've heard about the history of highly irregular graphs is a fun story. And I know it has nothing to do with the topic, but you know, math shouldn't just be about math. It should be about culture and learning the stories. And so there was a mathematician wanted to work with Paul Erdős, because who wouldn't want to work with Paul Erdős and get that coveted number 1? So he went to Ron Graham. Said, Ron, what do I do? I want to work with Erdős. And Ron said, well, you know, Erdős, he likes to work with people. It's not hard, just come up with a problem and tell him, and he'll oftentimes, you know, work with that. So the mathematician went away, thought about it, came back to Ron. I can't really think of a problem. Do you have any other advice? So Ron said, well, think of a topic. The mathematician went away, came back. I can't think of anything. Do you have any other advice? So Ron said, think of a word. And so this particular mathematician was known to often use the phrase when they were speaking, this is highly irregular. Okay, highly irregular, that's your phrase, that's your word. What does that mean? Well, we know what a regular graph is. What's a highly irregular graph? You know, and that was sort of the impetus of it. And now there's been many papers written on the subject and whatnot. And it's just like, I just want to work with Erdős. All right, take the phrase highly irregular and make something of it. And you know, so you never know. You never know. All right, good. I will mention there's a few other things that we can talk about. Let's see. Well, we can talk about C5. I claim this is a strongly regular graph. And it is indeed a strongly regular graph. Well, this will not be the last time we talk about C5 today. But what are the parameters?
5.
Okay, 5, good. 2, yes.
0.
0.
1.
1. 5, 2, 0, 1. All right. Should we do one more?
Peterson, is it something?
Did you have a question? Or?
Yeah, I have a question. So
Sure.
It's not fully formed because I
That's all right.
have trouble checking all the conditions.
Neither are my lectures.
But are if you have 2 copies of Kn, is that strongly regular? And they're disconnected. Like, can you have disconnected strongly regular?
Let's see. Can we have disconnected? I think 2 copies of Kn might be strongly regular.
I think that works.
I mean,
All of the non-adjacent things.
that's not very interesting.
It'll still just be 0 in the last.
Oh,
If you're non-adjacent, you'd have 0 common neighbors. So yeah, you could put 0, and then you could say, oh yeah, just 2 copies of, well,
Okay, so
but
these are not based on these 4.
right. There are cases where these 4 parameters will produce different graphs. Now, for small parameters, it takes time. So you start getting into sort of, I think it's design theory. It's like, okay, I'm setting up these sets of parameters. What can you tell me about it? So,
Yeah, I remember sitting in on the first day of design period, and the first thing we defined had 6 parameters. And I was just like, oh no, oh boy, okay.
yeah. Good times.
Good times.
All right, as we draw a Peterson graph, of course, we should say that there are many ways to draw the Peterson graph. This is the one I know by heart. Okay, so I claim it is strongly regular. So given that you believe me, which you don't have to, you can check it out very patiently, what would be the parameters?
10,
Good, 10 vertices.
3,
3 regular.
0,
0.
1.
And 1. Yep. All right. By the way, I will say there are other graphs that do not, you will not always have 0, 1 on the end here. And so there's a lot of places on the internet where you can find sort of compilations of like, here are strongly regular graphs. We should also mention that if you give 4 numbers at random, you're very unlikely to just have a strongly regular graph. There's lots of constraints that come into play. And so let's talk about some of those things. And, well, spectral graph theory, so we should talk about eigenvalues. So let's ponder upon that for a few moments. And to help us get there, so we'll think of eigenvalues, and so far we've done it of the adjacency matrix. We might introduce a new matrix in the next couple weeks. I mean, at some point we have to. There are other matrices besides the adjacency matrix. Let's look at A squared. And let's look at the UV entry. Okay, and what are the possible values that we can have for A squared? So there's a couple of things. We could have U equals V, U is next to V, and U is not next to V. And I claim that we can talk about these entries. So, should we start with U equals V? What do you have?
Degree.
The degree. Good. So that's K. What if U is adjacent to V? So we come up here, U is adjacent to V. How many walks of length 2 from U to V? It's lambda. And mu. Good. So, all right, so we already are starting to see things that we say, oh, okay, so we have essentially K on the diagonal, lambda in the places where coming from the adjacency matrix, and mu coming from where there used to be zeros in the adjacency matrix. And so it's like, okay, all right. So if you were to break this down, and this is probably not the most elegant way to think about it, but you'd say, okay, U equals V, this is the identity. That's the part of the matrix. And U adjacent to V, well, that's your adjacency matrix. And U not adjacent to V is everything else. That's J minus A minus I. So we can rewrite this and say that, oh, well, that says A squared is K times the identity, because we have K times the identity, plus lambda times A plus mu times j minus A minus I. All right, well, let's move things around. So we have just a single A squared, all right, that's fine. Now here we have a lambda A, and then we have a minus mu A. And then we're going to bring it across. So when we distribute the mu through, group the A's and bring them across, it will come across as a mu minus lambda times A. And then we have a minus k times I, and we'll leave mu, oh, whoops, sorry, not minus k times I. I got ahead of myself because I forgot about the minus mu I here. So it's secretly minus mu, and there's a k, so it's going to be a plus mu minus ki. There we go. And that is equal to mu j. All right. Now, can we get the eigenvalues from what's written on here? Yes, we can. When Steve asks a question like that, the answer is yes. All right, what's the easy eigenvalue? And why is that easy?
I forgot, but because I memorized it.
It's k regular. So we know the easy eigenvalue is k. Now, what do we know about our easy eigenvalue? Since it's k regular, it comes with the eigenvector that's all ones. So what do we know about the remaining eigenvectors? They're all orthogonal to the all ones, which is good. Okay, so now let x be an eigenvector that's perpendicular to the all ones. And we multiply both sides through. We get a squared x plus mu minus lambda ax plus mu minus k ix equals 0. Good. You've mastered the game. Perpendicular to all ones gets us 0. All right. Now, we said this was an eigenvector, so what happens to a squared x? Lambda squared. How about the next piece? Oh, I shouldn't use lambda. All right. Well, what should we use for our eigen? Alpha. You're right. Alpha squared. Alpha x, and then of course just x. And you pull out the x, alpha squared, plus mu minus lambda alpha, plus mu minus k times your eigenvector equals 0. But of course, eigenvectors can't be 0, which says, lo and behold, this has to be 0, which means that all our remaining eigenvectors have to satisfy a quadratic. This is probably feeling really familiar. So that's right, because math may not always repeat itself, but it often rhymes. So we use the same techniques over and over again. So, if you want to be a great mathematician, you just learn like 2 or 3 techniques really, really well and apply them better than anybody else can, and you'll be a great mathematician. Your worldview will only be through those, you'll walk around with your 2 hammers, but they're going to be huge, Whereas most mathematicians, they have just like a small collection of tiny little mallets that can't really break anything. But all right, we digress. All right, so alpha equals negative the coefficient here, and so I'll write that as lambda minus mu when we negate it, plus minus the square root of, again, that middle term squared, lambda minus mu squared, minus 4, AC, so 4 mu minus k, all over 2. All right. Good. Good. All right. We'll write those again on this next page. So, our eigenvalues we said we had k. We have lambda minus mu plus the square root of lambda minus mu squared minus 4 times mu minus k. And we have, all over 2. And lambda minus mu minus the square root. Lambda minus mu squared minus 4 times mu minus k all over 2. So those are our eigenvalues. And we can even talk about our multiplicities. And we'll assume connected, just to make life easy. Multiplicity of k is 1. That's Baron Frobenius. Once we're connected. Now the other ones, we can do the same sort of tools that we've done in the past, which is to say, we know the sum of the eigenvalues has to be 0. We know the sum of the squares has to be the number of edges. We know how many vertices we have. We know how many edges we have. And so we plug it through. We very patiently work it out. Or we say, well, somebody did it before, and we just copy what they did. So I have it on my notes here. So this is not me doing it in my head, just to be clear. But you probably knew that already. So 1/2 times n minus 1 minus 2k plus n minus 1 times lambda minus mu. Divide that by the square root of lambda minus mu squared plus 4 times k minus mu. And then the other one is similar, but with a plus. And so we have our lovely expressions. All right, nothing that we haven't done before, and that if we were really patient, we could, of course, rederive this again. Okay, so there we go. Now, I noted that not all values of parameters will result in a graph. Notice in particular, you have a square root. So what has to be true? It has to be a square inside, right? Because you can't end up with an irrational number of roots. You can have crazy eigenvalues. You can't have crazy multiplicities. And so that says the inside part must be a perfect square. So that can be used to eliminate possibilities and say, okay, we know that these things don't work. It doesn't, so it rules things out, but it doesn't by itself automatically rule things in. That's unfortunately a lot of spectral graph theory. It rules things out, but it doesn't always rule things in. Okay, well, we should do the most famous result in spectral graph theory when it comes to strongly regular graphs, which is we should talk some more graphs.
Why does it have to be a perfect square? Because the top is dividing by it. The top is 5.
But it's a square root.
Yeah, but if the square root of the thing is like 2.5, and you have 5 over 2.5, that's still a full number. 2.5 squared. I mean.
Well, the inside, lambda, mu, and k are all integers. So I think if you have an integer, I don't think you can take the square root of an integer and get 2.5.
Yeah, that's fair.
Mind you, I'm not a number theorist. We don't have a number theorist anymore. If.
Either integer or irrational.
Yeah.
Aha, cool. All right. So what's the basic structure of Moore graphs? So the idea of Moore graphs is you have this sort of growth. And you start with the root, and you choose a value, a degree. What degree should we pick? 3? All right. So you make your root degree 3, and so then you have 3 children, and you say, okay, I want each of these to have degree 3. So you already have degree 1 coming in, so then you have degree 2 going out. And you can actually grow for a while. And so more graphs as they are, you could have several layers. So you just say, okay, you could add 2 more and add 2 more and add 2 more. But we're interested in more graphs, and in some sense are minimal. So what do we want? Well, we want them to be regular. We want them to have a min number of vertices. And we want them to have girth 5. So remember, the girth is the smallest cycle. All right, so here, after I've gone down 2 layers, I want to stop. Do you have a question? Or? Why 5? Because it really fits the narrative for what's going to happen.
So is girth 5 like how more graphs are defined, or is it just for now this is what we want?
So in some sense, we're after the smaller more graphs. So more graphs, my understanding, but you can always look up and find out more, is to say that you can go several layers, and on the bottom layer you're going to link things in. So for instance here we could try to link things in. I think if we link, let's see, I'm probably going to get this wrong, and so my apologies. So by linking things in a smart and clever way, you can get interesting graphs. So here I've added some stuff downstairs, making it degree 3 for these vertices as well. So you go down 2 layers, add stuff in, and just to make sure that you maintain these various pieces. Because you could, of course, do silly things like add an edge over here. Well, that would make a triangle. And you want to avoid silliness. And so it's like, okay, how do you make sure to avoid silliness? All right.
What is the generalized form here? Is it just that it's you have a root with some number that's going to define your degree?
Right. You have a root with some number.
Everything's split
Yep.
twice.
You go down 2 layers, you close it up. That's what we're after. People are highly skeptical about my it is the Peterson graph. Yes. Yes. Now, why did you suspect it might be the Peterson graph?
Because last semester, a grad student told Alice and I, not a grad student, it was Henry, told Alice and I to find the graph what is it? It's degree 3 and no vertex is more than the maximal graph that has degree 3 and no vertex is more than 2 apart.
Okay.
We came up with
And
then
we
he's
came
like,
up with
well,
that, but we had told him at the very beginning. We said, he said it's a kind of famous graph, and we said, oh, is it the Peterson graph? And he's like, no. So it was like half an hour, and we ended on that, and he's like, yeah, it's the Peterson graph. It's burned into my memory.
Lies! It was all lies! So, okay, all right. So it turns out that what we're actually searching for is a very particular type of strongly regular graph. So let's, for now, we'll call K our degree, and I want to fill in some other pieces here. Can we figure out how many vertices we have? Well, there's one vertex on the top layer.
N times
And
K
then
times K plus 1.
Yeah, so downstairs there's K times K minus 1. So that's K squared minus K. Add K, add 1.
So it'll be k times k minus 1 to the something.
So it'll be k squared plus 1. So for this point, we're only going 2 layers.
Okay.
Because we don't want to, because we want it to be strongly irregular. So we don't want to keep going down, because if we go down too far, then we're not going to have things which are we're not going to be able to satisfy being strongly regular.
I'm going to be able to loop back together.
Because we'd have vertices which are 3 steps apart if we stopped after 2 layers. Sorry, if we went further than 2 layers. All right. What about lambda? So remember, lambda is take 2 adjacent vertices. How many common neighbors do you have?
0.
0. Why 0? What about our construction says? If I take 2 adjacent vertices, they have nothing in common. Yes, correct. Because if I have 2 adjacent vertices and they have something in common, that's a triangle. And so I can't have triangles if my girth is 5, because the smallest cycle I can construct is the 5 cycle. How about mu? So remember, this is non-adjacent vertices. How many common neighbors can a pair of non-adjacent vertices have? Should be at least 1, by the way. So I'll give you a lower bound of 1.
You have 2, that would give you a cycle with 4.
Good. If you have 2, you'd have a 4 cycle. Because what can you do? Well, I'll come back here. If we had 2 down here, we could jump down, up, down to the other one, back. So that's a 4 cycle. So this is a 1. All right, so more graphs. Do they exist? Do we know anything? Well, we can go even more than 1, at least 2, right? Because the 5 cycle also satisfies it. So we have a 5 cycle and a Peterson graph.
Oh, interesting.
So, are there more? Okay, so that's our goal. In the remaining time that we have, we will try to say definitively yay or nay as to whether or not there are any more. Okay, so we run the process like we did before. Well, we don't have to run the process like we did before. We have our parameters here. We have our n, k, mu, and lambda. And so what we can do is we can actually talk about what our eigenvalues are. So for instance, lambda minus mu is 1, mu minus k, is minus k. And so if we are very careful here, and I don't make any mistakes, then what we have is that our 2 eigenvalues, we'll say alpha 1 is minus 1 plus the square root of 4k minus 3 over 2. And then alpha 2 is minus 1 minus the square root of 4k minus 3 over 2. Okay, I really messed that one up. So alpha 1 and alpha 2. Minus 1 plus minus. There we go. And for reasons, just to make it a little bit easier for us to play around with things, we'll write this as plus or minus the square root of capital D over 2. Okay. Now, our goal is to say something. We already said that, well, look, you have some constraints because you have square roots. So the square roots are going to force certain things to work or not work. And so we're going to try to get that out. Okay, so, well, what are some things we can say? So let's say alpha 1 has multiplicity m sub 1, alpha 2 has multiplicity m sub 2. First thing is, if I add m1 plus m2, what's the result? So add these two together. What do you get?
K squared.
Add these two together.
N minus 1 for that.
N minus 1, yeah. Because essentially it's everything but this one eigenvalue. So m's are multiplicities. And so it's just saying, okay, we know we have one eigenvalue, that's the degree, and then we have everything else. And so these are the everything else. All right, we will actually use this equation. Okay, good. And I think someone said k squared, so I should have written that down. All right, so now we have m1 plus m2. What would happen if we took m1 times alpha 1 plus m2 times alpha 2? What would that be?
Negative k.
Negative k. Why?
Because m1 alpha 1 plus m2 alpha 2 plus k is all the eigenvalues 0.
Right. It's essentially the trace. So instead of like alpha 1 plus alpha 1 plus alpha 1, we just said, well, it's m1 times alpha 1, and so forth and so on. Well, you notice that our our alphas have 2's. Those aren't nice. So let's double this. Aha. So it turns out that 2 m1 alpha 1 plus 2 m2 alpha 2 is minus 2k. True story, true story. Now, we can replace our alpha 1 by, well, 2 alpha 1 is minus 1 plus root d, and similar, 2 alpha 2 is minus 1 minus root d. So, m1 times minus 1 plus square root of d plus m2 times minus 1 minus square root of d is equal to minus 2k. All right. So we'll move this up. We'll still be playing around with these expressions for a few moments, so we won't move them too far. Let's see, what do I need? I think I need at least that part. All right. So far, so good? Any questions? Doubts? Concerns? Do people know what the punchline is that's coming? Some people do, some people don't. All right, good. So some people are going to be surprised. Ha ha ha. All right, well, let's see, where are we? Let's rearrange this. And so what we can do is we see, well, there's some parts that have a square root of d, and then there's parts which don't. So if we say, well, what has the square root of d? There's an m1 square root of d and a minus m2. So we can say m1 minus m2 times the square root of d, and then everything else. So okay, so move that to the other side. We have a minus 2k, and then we have a minus m1 and a minus m2 that move across, so that's a plus m1 and a plus m2. Well, but we know what m1 plus m2 equals, because we wrote it down. Equals k squared. So this is k squared. All right.
Minus 2k.
Oh yeah, minus 2k. Very dramatic pause. It probably won't be my last dramatic pause for today. So, what would happen if square root of d is irrational? Because that could happen.
Well, m1 minus m2, that's an integer.
Right.
Integer times irrational equals integer.
Integer times irrational equals integer. Is there any way that can be true?
No, because if you divide over the integer, then you get irrational equals rational.
Ah, but there is a case when you couldn't divide.
Then m1 equals m2. That's
Right.
the case.
This would imply that m1 equals m2, which really implies that the left-hand side is 0. Well, so that says k squared minus 2k equals 0, or k equals 0, or 2. Well, 0, not very interesting. 2. Now 2 is the candidate. So can we think of a graph too regular graph.
Just the cycles.
Yes, this is C5. Yeah, so C5 is one of these graphs. Okay, so that's if square root of D is irrational, and that's the only graph that works. So, okay, so now we know something. Now we know that the square root of D has to be rational. Great. So, what does that tell us? Well, it tells us that if I look at D, and remember D was shorthand, and unfortunately I took it off the screen, but D is this 4k minus 3. So D, which is 4k minus 3, has to be a square.
Where did we get that from?
The 4k minus 3 is this part. So D was just shorthand for 4k minus 3.
Right, that was the simplification of the.
We just gave it a name.
So D was just a temporary
Alpha one
name.
and Alpha 2, yeah.
Yeah, so alpha 1 and alpha 2 are the eigenvalues.
Yeah.
And we're basically saying we know things about the eigenvalues and we know things about their multiplicities and what consequences have to follow. All right, so here we go. Since we have D is 4k minus 3, which is s squared, that tells us that k, we can solve for it. We add 3 divided by 4. So we have s squared plus 3 over 4. Now, we're going to plug stuff in. So we have m1 minus m2. What can we do with the square root of D? It's s, because it's s squared. Okay, that equals, on this other side, k squared minus 2k. But I can replace k in terms of s. So we have s squared plus 3 over 4 minus 2 times s squared plus 3 over 4. And I square the first term. Well, because I'm nervous about fractions, in addition to forgetting to write squares and other things, I'll multiply through by 16 because 4 squared downstairs becomes a 16. 16 times m1 minus m2 times s. S squared plus 3 quantity squared, and that's s to the 4th, plus 6 s squared plus 9. Here, 16 goes divided by 4, leaves us with 4. Times 2 is 8, so that's minus 8s squared, and minus 8 times 3 is minus 24. Now 9 subtract 24 is negative 15. Move that to the other side. That's 15. Move this, so I'm moving the constants, and then moving the left-hand side to the right. So we have s to the 4th. 6s squared minus 8s squared. That's minus 2s squared. And then plus 16 times m1 minus m2 times s. Which should have been a minus, not a plus. All right. What do you notice about all these terms now on the right-hand side? S in common. So s times s cubed minus 2s minus 16 times m1 minus m2. And remember, the m's are multiplicities. They're whole numbers. So s is an integer. S cubed minus 2s minus 16 times m1 minus m2 is an integer. And you multiply these two integers together and you get 15. Now we use very simple number theory and say, hey, s divides into 15. So, can we come up with numbers that divide into 15? What are they?
1, 3, 5, and 15.
1, 3, 5, and 15. Okay, so for each value for s, remember there's this expression for k. So plug in s equals 1. 1 plus 3 is 4, divided by 4 is 1. All right, is that going to possibly work for us? No.
Do we have plus minus in the s's? Could they also be negative?
Now we'll assume it's a positive s. We're just saying that the inside is a square. So you might as well say it's a positive. So you can't work for 1. All right. If we have 3 squared plus 3 is 9 plus 3 is 12. 12 divided by 4 is 3. Is there a 3 regular graph that works? Yeah, this is Peterson. Okay, cool. Plug in 5. What do you get? 28 over 4 is 7. Is there a 7 regular graph that works? Now, you probably don't know the answer to this off the top of your head, and the answer is yes. It has a name. It's called the Hoffman-Singleton graph. And Hoffman and Singleton are the ones who first figured out what kind of graphs we had. Now, if you plug in 15, what will you get? 57. That's nice.
Then who knows for 57?
Now, is there a graph of degree 57 that works? And the answer is nobody knows. See, dramatic pause. Yeah.
No one knows?
No one knows.
That's a big graph.
This is unknown if it exists.
Yes.
Because remember, this is just the degree.
Yeah, exactly.
You have to square it and add 1 to get the number of vertices. K squared plus 1 is the number of vertices. So the problem is, that's a lot of vertices. So it is true, it's a finite problem. It's either yes or no. And so in theory, one could look at all graphs. In principle, you can't. So
So is there either 3 or 4 of these?
right.
Is that what that means?
Yeah, so if you count the 5 cycle, 5 cycle of Peterson, Hoffman, Singleton, and there's beautiful pictures if you go to Wikipedia for Hoffman, Singleton. I can't draw it. I mean, I could, but it would just be a big dark mass of marker. But yeah, there's lots of papers on this graph, by the way. And so there are people who say, well, if this graph exists, it must satisfy this. And it must not satisfy that. So there's lots of properties that are known about this graph. It might be that people have proven things about a graph that doesn't exist. And of course, it's very easy to prove things about the empty set, but we don't know. And unfortunately, computational tools are not the way to solve it.